Hello, my name is McGuire Hodson, and this is my lab report for the Lab 1 constant velocity. So, the purpose of this lab was to observe the motion of an object with constant velocity, analyze the data using tracker software, and compare it with a computational model that was programmed based on starter code. The lab is based upon Newton's first and second laws of motion. The first law of motion being that an object will not change its motion unless acted upon by a force, and the second law of motion being that force is equal to mass times acceleration. The computational model depicts the expected motion of an object experiencing no net force, so the motion would be constant velocity. The analysis displayed the object's position time graph as almost perfectly linear, which matches the model's predictions closely and confirms the concept of constant motion, both in theory and in reality. To validate the results of the experiment, a computational model was programmed using VPython. It follows the equation for Newton's second law, which is force equals mass times acceleration. In the program, the object, in this case a ball, starts at a position of 0 meters and a velocity of 2 meters per second. The position updates using the equation final position equals initial position plus velocity times the change in time. The assumptions for this model are that friction is negligible, no external forces affect motion, and that the time intervals are small enough to provide accurate values. The model also follows Newton's first law, which again states that an object in motion will stay in motion, and an object in rest will stay at rest unless acted upon by a net external force. This model is used because it can predict motion in a hypothetical vacuum, and it shows how close the experimental data fits the prediction. The laws are used because these laws are also followed in the experiment. And so these two animations show Newton's first and second law, with the first animation showing the ball rolling and not stopping because no net external force is acting upon it. So in this experiment, the system being analyzed is a moving toy car on a track. Well, the surroundings are the environment, which include air resistance, friction, and the lab room itself. For the experiment, the object is pushed along the track with an initial velocity around 2 meters per second and a position of 0.000469 meters. For the model, the object has an initial velocity of 2 meters per second and an initial position of 0 meters. The experiment involved pushing the car and measuring both the time and the distance it traveled along the track. The coding for the computational model involves starting the ball at the aforementioned initial conditions, as well as computing its final velocity and position. The mass of the ball is 1 kilogram, and it travels at a constant velocity with no net force acting upon it because it is in a vacuum. And so this is the relevant code that was used to output the model. And then the bottom picture shows the experiment setup. After collecting the data using Tracker, the motion closely matched the theoretical motion that was given using the computational model. The position versus time graph showed the motion as linear, with a correlation coefficient of 0.995, which is very high, indicating a strong correlation. So, the experimental data and computational model both produce linear position time graphs, confirming that the motion of an object with no net external force is constant, both in theory and reality. Of course, no net external force is impossible in reality unless the object is in a vacuum. So this is expected based on Newton's first law and the momentum principle. However, although the experimental graph was mostly linear, it was not perfect. This is because, again, the car was not in a vacuum, so there were forces acting upon it, including friction and a net force upon pushing the car, as well as air resistance. Additionally, there may have been some measurement inaccuracies in the tracker software. These are to be expected because all systems not in a vacuum experience net external forces. So, despite the errors in the experiment, the overall motion of the car was consistent, which supports the idea that no net force results in constant motion. If the axes were flipped, all position values would be negative, and velocity would also appear negative. However, the results would be the same, as the velocity vector would have the same magnitude, because magnitude is an absolute value. The forces that give zero net force are the combination of gravity and the normal force. For example, a moving car on a frictionless surface would experience no net force and constant velocity, despite still experiencing gravity pushing down on it and normal force pushing up on it. Overall, the lab successfully demonstrated constant motion with no net external force using a combination of experimental data and a computational model. Both the tracker data and the VPython computational model showed a linear position-time relationship, reinforcing both Newton's first and Newton's second law. And so that is the end of my lab report.